Hi friends, this is Dr. G. Srinivasa Gupta, Professor from Department of Mechanical Engineering of VIGNANA Institute of Engineering Technology. As a continuity in the course Dynamics of Machinery, we are going to discuss today partial or full balancing of reciprocating masses. In previous lecture, we have seen how this reciprocating masses arises. We have taken simple slider crank mechanism which is used in IC engines. So the displacement, velocity and acceleration of the reciprocating element which is called piston is derived in the previous session. We again let me just recollect those velocity acceleration of piston. As we know that just simple slider crank mechanism, this is the crank which is connected to the crankshaft, it is rotating, and this is the connecting rod attached to the piston, and piston is reciprocating in the cylinder. This is the configuration of slider crank mechanism you have seen. As piston is getting displaced, then the acceleration of piston, because piston is reciprocating in the cylinder, along the center line, then the acceleration of the piston can be derived starting from displacement of the piston with refer to, because this is the crankshaft is rotating in the bearings, with refer to crankshaft, we can take this distance of the position of the piston is x we have taken, and we can write x equal to, when crank is at this position, crank is an inclination with the line of center line or center line of the cylinder is theta, and connecting rod some angle pi if you say, and length of connecting rod we have taken L, and length of crank we have taken R. It is the notation. So then the displacement of the piston or the position of the piston from this crankshaft fixed frame, then that is x. X can be written as r cos theta plus square root of L square minus, because this length r sin theta. So square root of L square minus r square sin square theta is going to give this value. So position of the piston at this configuration, at this inclination of crank is r cos theta plus L square minus r square sin square theta under square root this length. So this is the x. When the piston is at top dead center, then the crank as well as connecting rod is going to align with the center line of the piston. This is the R, this is the L. Then we can say this R plus L is the position of the crankshaft or frame. So this is the R plus L, position of the piston. This distance. So when piston is going to displaced, then let us say this one is x, this R plus L is some x dash position. If piston is at top dead center, piston. Then displacement, how much displacement given by this piston is by pressure force sitting, and piston is going to be moved toward inner dead center, then this is the displacement given. If you want, write x dash minus x is the displacement of the piston given, some x double dash or something displacement expression, that also we can write, and we can differentiate this displacement with respect to time. You will get velocity of piston, again acceleration dv by dt. So you can have those expressions as we have seen in the previous lecture also. So these are the things, x dash L plus R when piston is at top dead center, and x dash minus x is the position which is just I have shown. This is the position x of the piston. Then amount of displacement given to the piston is x dash minus x. That is we can have, we can see that is x dash minus x equal to r into 1 minus cos theta plus r square by 4l 1 minus cos 2 theta. Here two terms are there. Okay, if you find acceleration, then you are going to get r omega square cos theta plus cos 2 theta by L by r. So the acceleration of piston is towards inside. Okay, acceleration of the piston. So inertia forces, because of mass of the piston, inertia forces are opposing direction, positive x direction. That's why we are going to take this inertia force F is mass of the piston into r omega square, this acceleration. So because as per D'Alembert's principle, we know that D'Alembert's principle tells that inertia forces and plus whatever external forces must be balanced. So this is because the inertia force, acceleration force of the piston is opposite x direction and inertia force positive direction. So we could write inertia force mr omega square cos theta plus cos 2 theta by L by r, cos theta plus cos 2 theta by L by r. L by r, sometimes we will use the notation n. Okay, so I think you are able to understand. This inertia force consists of two quantities. One is mr omega square cos theta. Second one is mr omega square cos 2 theta by L by r. So these are two forces, inertia force, which need to be balanced. So how we could be able to do, what are the this balancing can be, how we can able to make this balance, how far we are able to achieve complete balancing or partial balancing, we will see. So in machines like IC engines, compressors and pumps, always there is a component called piston having reciprocating motion. These mass of the piston produce unbalanced inertia forces due to acceleration, as we have seen just now. Okay, unlike rotating masses we can have complete balancing. But in case of this reciprocating masses, complete balancing is impossible because motion is not circular, acceleration is not uniform, because sometimes direction reverse, when piston is going to move in reverse direction, then there is different speed or acceleration. So acceleration is changing continuously, moving up and down. So how we can going to balance these forces, we are going to see. So these inertia forces are two components. Primary force is, we can say Ft equal mr omega square cos theta. This is same frequency as crank rotation, dominant component. This is actually. And secondary force, we have seen twice the crank frequency, because it is have written 2 theta. Okay, smaller but significant in high speeds. So we will see the part of balancing in these two forces. So as you know that this is the, okay, as I mentioned, then balancing we need to do. Okay, what are the primary forces? Primary forces, this is acceleration forces, this one mr omega square cos theta you have seen. Let us talk about primary force first. Then inertia force is in this direction. Okay, same magnitude is same, inertia force Fi. Okay, primary inertia force Fp I can write. Secondary we will talk about, okay, once we see how we can balance it. So as in the previous lecture also, just I have, okay, communicated that if this is the inertia force, okay, if we want to try to attach equivalent mass which gives, okay, mr omega square, okay, magnitude, and this angle made by crank is theta, obviously this is theta, then these inertia forces mr omega square cos theta at this position, okay, can be balanced, but there will be unbalanced component of this mass attached here, rises again mr omega square sin theta. So that is again unbalanced force rises additional because of this trying to balance this mr omega square inertia force cos theta, mr primary force, inertia force. So this leads to some wobbling of the crankshaft up and down. So this is also big problem. So we will come to the compromise that we try to use some fraction of the force of the primary force balancing. Okay, then we will use only the fraction C, let us say, fraction of this force. So C generally varies 0.5 to 0.75. So if you balance this much only, C multiplied by mr omega square cos theta, then the unbalanced one is, then the unbalanced one become unbalanced force, unbalanced primary force, unbalanced. Okay, primary force is 1 minus C into mr omega square cos theta. Okay, what is the effect of this unbalanced primary force? The effect is, okay, this force causes this unbalanced primary force, as well as there is a horizontal force causes FHC. Okay, we are going to balance this much, but while balancing this C mr omega square cos theta, there will be a component of that, as you know, that C mr omega square sin theta will be the again in unbalance force causes swaying force. This is called swaying force, which leads to engine vibrations. In case of, if two cylinders are placed parallel, okay, apart, then this leads to this unbalanced force, that is C mr omega square sin theta leads to, okay, two cylinders are placed, then it leads to coupling. Okay, with respect to this plane, one cylinder here, second cylinder, let us say. So this leads to couple with respect to other plane. This is called swaying couple. This is unbalanced force into distance. Okay, this distance. So this is also results in rocking motion of the engine. Engine will rocking effect motion because of this couple. Now balancing of, in case of multi-cylinder engines, there is some advantage. Okay, we can have complete balancing. Antically we can write equation mr cos theta. You have seen mr omega square cos theta, okay, and mr omega square sin theta. Okay, so you can do it unbalancing mr omega square cos theta by, okay, arranging this multi-cylinder engines cranks such a position that they are going to give opposite components, so we can balance. Okay, but condition for complete secondary balance also, if we want to see, we can write mr cos 2 theta by L by R. So this is to be required to be 0. Let us see whether it is possible or not. Suppose cranks are arranged in opposite direction. Cranks placed at specific angles, then these are at 180 degrees. In two cylinder engines 180 degrees, and in case of four cylinder engines, two cylinder engines, these cranks are placed 180 degrees each other. If crank is in this position in the two cylinder engines, then or four cylinder engines, in case of four cylinder engines, this can be placed 90 degrees each other. So then it is possible to balance primary forces. So in case of opposite cylinder engines, pistons move in opposite direction. Example, boxer engines. So there we can have excellent balancing. This is actually excellent balancing. Okay. So in V engines also, cylinders inclined at an angle reduces unbalanced forces. These are the types of arrangement of cylinders such that cranks making an inclination with each other. In these all cases, we can easily see that the balancing can be made without any unbalanced forces, because as you have seen, suppose in this case, if I attach this, okay, this is the crank, okay, this is unbalanced mass, balancing mass I am attaching mr omega square cos theta, I said, okay, then this creates some swaying, this leads to swaying couple mr omega square sin theta also, mr omega square sin theta. Okay, another cylinder, if you place crank like this, then attach this mass, then what happened? This is, okay, mr omega square cos theta will be balanced. With that you have seen in the piston, it will give the directions. Okay, and sin theta, the sin theta is goes to in because if you arrange this direction, then mass is attached in this direction, then obviously this component is going to be balanced with this. So complete balancing is possible for primary forces only. Okay, these are the various arrangements: crank arrangement, opposite cylinder engines, and V engines. This can be possible for balancing completely of primary forces. Okay, this is the balancing how primary forces. Yes, we can balance only fully in multi-cylinder engines only. For single cylinder engines, it is not possible to balance. There is a result of swaying couple, as you have seen. So how do we balance? By proper arrangement of cranks of each cylinder. Okay, in secondary force, as you have seen, it is difficult to maintain balance because this is some amount only we can balance. Okay, so this occurs in locomotives when balancing mass is added, that leads to hammer blow. See, suppose the balance MR, okay, as you have seen, this is the mass attached. Okay, this is the component MR omega square sin theta is unbalanced force. When crank is at an angle of 90, what happened? It is dominating. This one will dominate because it becomes MR omega square. This leads to hammer blow. That is MB is mass of mass attached balancing mass. Okay, this leads to hammer blow. So lifting of the wheel from rail is damage to the track also. So this is the effect of unbalanced force which leads to hammer blow. Okay, if theta is 90, crank angle theta is 90, then we have only MR omega square term. So what happened? That balancing is not possible, piston actually. This leads to hammer blow. And variation of tractive effect, unbalanced horizontal force. If theta crank is at theta angle, there is a horizontal component of this is unbalanced. This leads to fluctuating force on rails, leads to vibration. Okay, you are able to understand in case of single cylinder engines. Okay, so what are key design consideration we need to take? Choose optimal balancing. That means C value while choosing the fractional amount of balancing mass required is need to be understanding the complete design, how we can take the optimal value of C. So okay, it should minimize swaying force, that is leads to swaying couple. So optimize crank angles, but we need to use multi-cylinder arrangement only. So what are the important points you need to understand? Complete balancing is impossible. Primary force is dominant. Secondary force is high frequency disturbance. Primary force leads to dominant because the value you have seen. Okay, if you write L by R, secondary force is what is that? MR omega square cos 2 theta, MR omega square cos 2 theta by L by R. L by R is what is the value? Always it is 4 to 6 its range in general engines adapted. So it is magnitude is very less. Okay, compared to primary force. That's why primary force is dominant and secondary force is high frequency disturbance. Frequency, high frequency 2 theta you have seen. Okay, partial balancing introduces new forces. Obviously, you have to attach another mass that leads to partial balancing. In multi-cylinder engines, you can improve the balance. Primary forces can be balanced. Okay, a lot of improvement is there. But secondary forces cannot be balanced. Okay, so single cylinder engines, high vibration. Multi-cylinder engines, smoother operation. As you know that primary forces can balance. And opposite engines also, best balance is possible. Okay, so this is all about how we can do the balancing. What are the effect of unbalanced forces? That is swaying couple, hammer blow, and tractive effect, as we have seen, variation of tractive force. Okay, these are the effects. So how do we, for a given specifications of the engine, how do we make that balancing properly or partial balancing? We can come to the partial balancing level. We will take some numerical exercises and we are going to discuss on this concept again in numerical exercise problems in our coming lecture. Okay. With this, this is the concept entirely effect of unbalanced primary forces and secondary forces we will see more elaborately in numerical problems. Okay, so but primary balancing is complete balancing is may be possible by multi-cylinder arrangement with proper crank arrangements, and secondary forces balancing is not that much easy because high frequency vibrations it leads to any unbalancing mass. Okay, with this I am concluding this lecture here. We will see more elaborate and more detailed understanding by considering taking some numerical exercises in our coming lecture. Thank you one and all.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.